Hello everyone. What we'd like to do in this section 2.8, is we want to start talking about inverse functions. So the things that we're going to talk about in this video specifically is what is an inverse function and how do we find an inverse function. Let's lead with an example. Let's say, let's give ourselves a little bit of room. So let's say, for example, that we have the function f of x, which is equal to 3x minus 5. Now, a great way to think about any function is it's a mapping. I'm taking certain members of what we call the domain, I'm plugging those in, and I'm getting an output, which we call the range. And let's sketch that. So whenever we're thinking about a function, we think about members of its domain. These are all the inputs. And these values, these x values, are getting mapped to a new set of numbers, which we call the range. So, for example, let's say we have 0. Let's say we have the number 0 in the domain. And now let's evaluate that into f. Let's plug 0 into f. And let's see what our output would be. When I plug 0 into f, it takes that number, it multiplies it by 3, and it subtracts 5. So 3 times 0 is 0. 0 minus 5 is negative 5. So 0 gets mapped to negative 5. Let's plug in another number. Let's say, I don't know, let's say we plug in 2, for example. Let's move it right here. Let's do 2. If we plug in 2, let's see where this gets mapped. If we plug in 2, it looks like 2, 3 times 2 is 6. 6 minus 5 is 1. So this is going to get mapped to 1. So when I evaluate f at 2, we get an output of 1. We could go further on with this if you'd like. But what we would like to be able to do in something interesting is I'm going from the domain to the range, but I wish there was another function that would bring me backwards. I wish there was some function, kind of maybe I'll call it a backwards function, that if I were to evaluate this function, let's give it a name. Let's call it the inverse. So we put an f and we put a little negative 1 at the top. And if I were to evaluate this function at negative 5, what it would be nice is if I plug in a negative 5, I would want to get to 0. So let's write what we have so far. What I know for my function f, if I plug in 0, I get an output of negative 5. And what's special about the inverse is if I took this backwards function and I evaluate at negative 5, I want it to bring me back to 0. It's doing the opposite thing. It's kind of like, I'm multiplying by 3 and I'm doing the opposite thing. I'm dividing by 3. I want to be able to somehow figure out how to go backwards. Similarly, if I take a value, let's say, I don't know, if we took 2, we got an output of 1. Now what would I want the other function to do? What would I want the backwards function or the inverse function to do? Well, if I plugged in 1, I would want to get an output of 2. In general, if we have some value we plug in into the domain, let's say, let's draw this. If we plug in 1, we want to get the output of 2. If we plug in 1, we want to get the output of 2. But in general, if we plug in a value into the domain, let's just say we plug a. If we plug in a, and we wanted to compute, let's say, f of a, we're going to get an output, let's just call it b. So we would have that f of a would be equal to b. And now the inverse function would bring me back. So if we did f inverse of b, if I plugged b into the inverse function, that would bring me back to a. So f inverse of b would give us out a. This is a property that we want in this function. Now, we don't want to be able to just evaluate an inverse function just by looking at a table of numbers. I would like to have a formula for it. Notice here that, I have a nice formula for f. You plug in an input, you get out an output, but I don't want to just say, oh, the inverse function, I'm going to take this output and get back to the input. I would like to be able to find a nice way to come up with a formula for f inverse. So that's our new question. I'm going to erase a little bit of what we have here. Or let's just write it up here. So I guess question, how do we find a formula for the backwards function? How do we do that? Well, let's make a nice observation here. Notice here that if 0, -5, notice 0, -5 is on F. So if you plug in 0, you get an output of -5. Then -5, 0 is on the graph of F inverse. And we could kind of do this in general. If I do it with the A's and B's, we could say, well, if we plug in A and get an output of B, this would be a point on the graph of F. If AB is on F, then BA is on F inverse. The key thing to realize here, is that the X and Y values flip-flop. The X and Y values flip-flop. When I plug in an X value, I'd get out a Y value. If I plug in the Y value, I'd get out an X value. They flip-flop. This is the key observation. Really what's happening is the domain and ranges are flipping. So how are we going to find this formula? We're going to use this observation. How do we find a formula for this function? Let's think about it. Okay, well, what I have here is I have that f of x is equal to 3x minus 5. Let's go ahead and get out of function notation. Instead of writing f of x, we could write y is equal to 3x minus 5. So this is the domain. This is the domain of f, and this is the range. This is the range of f. Now what I want to do is I want to flip-flop these. I want this to be x, this would be x, and then I get a 3y minus 5. Because now, for my inverse, this is where my inputs are going to be, and now these are going to be my outputs. It's doing the backwards thing. I'd plug something in here, and I'd want to figure out the output. This is the inverse. This is f inverse. This is going to be the domain. This is the domain of f inverse. And this would be the range. This would be the range of f inverse. Or you could think this would be the input into my inverse function, and this would be the output. Well, this is written very awkwardly. Because I don't want to have to plug something in for x here and have to solve for y every single time. That would be tedious. So what we're going to do here is right when we flip-flop the x and y values, now we're talking about the backwards function, we're going to solve for y. Let's write this up over here. I wish I had a little bit more board space. But for the function f, we have that y is equal to 3x minus 5. Well, what about the inverse function? Well, the x and y values flip. The domain and range flip-flop. X is equal to 3y minus 5. Once we flip-flopped them, now I'm talking about the inverse function. Now we want to solve for y, so that'll be our next step. So let's go ahead and add 5 to both sides. So here I'll get, what, x plus 5 is equal to 3y. And now we can solve for y by dividing both sides by 3. So now I have that y is equal to x plus 5 all over 3. This is the inverse function. If I go back to function notation, this here is f of x, which is equal to 3x minus 5. These y's are different. This is now my inverse function. This is the inverse. And this is going to be equal to x plus 5 all over 3. This is the inverse function. How do we find inverse functions? We make the key observation. It's the backwards function. The x and y values flip-flop. So how do I find a formula for an inverse? I take the x and y values, I flip-flop them, and then I solve for y. That's how we're going to get the inverse function. Let's see if it works. Let's test it out. Okay. I want to keep this up here. We had that f of x was 3x minus 5. We have that the inverse function was x plus 5 all over 3. X plus 5 all over 3. Let's test it out. Well, notice over here, if we plug in 0, we get the output of -5. Well, look. What if I plug in -5 here? If I plug in -5, I get -5 plus 5 all over 3. I get 0 over 3. I get 0. I get 0. It's doing the opposite. Let's try another one. What if we plug in 2? If we plug in 2, we get what? 3 times 2. I know it's written right there. Minus 5. 6 minus 5, that's 1. Well, if we plug in 1, what are we going to get? We're going to get 1 plus 5 over 3. This is 6 over 3. Oh my goodness, it's 2. It's 2. It works. It works. We got our backwards function. Yes. Oh, whew. Great. It's working. It's working. Okay, so great. We have an idea of how to find a function and how to find its inverse. But before I go on to do a couple more examples of this, I would like to write down a key feature or a key observation that we have with these functions. So let's keep these over here. F of x equals 3x minus 5. And then we had its inverse. Its inverse was x plus 5 all over 3. Let's just kind of hold on to this. There's going to be a nice key observation that we need to make here, specifically with functions, their inverses, and composing them. Notice, for example, let's say I'm starting in my domain of f, and I plug in 0. 0 is going to map me to -5. But let's take that output and then plug it into the inverse. So I plug in 0 into f. That brings me to -5. That output gets fed into the inverse, which is going to bring me back to 0. Similarly, if we were to take f of 2, f of 2 is going to map me to 1. If I take that output and plug it into the inverse, that brings me back to 2. Also, let's say we do it the other way. Let's say we start in the range. This would be now the domain of f inverse. This would be the domain of f inverse. So I should write this. This is domain f. This is range f. This would actually be domain f inverse. This is what I plug into the inverse. And this would be now the range. This would be the range of f inverse, since I'm starting here and getting mapped here. So notice, if I started with something in my range, or I guess the domain of f inverse, if we plug in -5 into the inverse function, we get an output of 0. Now if I take 0 and I plug it back into f, I'm going to get right back to -5. Similarly, if we plug in 1 into our inverse function, f inverse, that's going to map us to 2. And if I plug 2 back into f, that's going to be, if I plug 2 back into f, that's going to bring me back to 1. So what are we doing? In this top row, I'm starting here, I'm going here, I'm going back. I'm starting here, I'm going here, I'm going back. Or the other way around, the bottom row, I'm starting here, I'm going here, I'm going back. I'm starting here, I'm going here, I'm going back. In general, what we should realize is that inverse functions undo one another. In general, let's write this up. I'm gonna write this up. This observation here is very special. It's called the fundamental property of inverse functions. They undo one another. It's like you take a number, you multiply by 3, you do the opposite thing, you divide by 3, you're back to where you started. What we've just realized here is something that's called the fundamental property of inverse functions. And this is why we care about them so much. This is why we care about them so much. Okay. The fundamental property of inverses. This is what it says. It says if you take a value x, you plug it into your function, you take that output, you plug it into the inverse, you're back to where you started. these functions undo one another. Similarly, if you took your inverse function and plugged in a value, that's going to bring you, I guess if you're thinking about f, that's going to bring you from the range to the domain of f. And then you plug it back into f, you're going to get back over here. You're going to get out x. When you compose a function and its inverse, they just undo one another and you just get back out the original input. Now we have to be a little bit careful. We have to be a little bit careful because these x's are different. These x's live in different spaces. Notice here, I'm evaluating f at x. So this x right here, so this case, this x is in the domain of f, because I'm plugging x into f. That's taking something from the domain of f, bringing me to the range. Now from the range, the inverse brings me back to the domain. This is a little bit different here. This x, I'm first applying it to f inverse. So either you can say that x is in the domain of f inverse, or similarly you could say this in two ways. You could say x is in the range of f, or you could say that x is in the domain of f inverse. Remember, the domain and range is flip-flop. So you want to be a little bit careful when applying this property. You want to think about where this x actually lives. So this is the fundamental property. Let's test it out. Let's test it out with that example we did earlier. I'm going to go ahead and erase this. This is a great way to check your work also. Let's go ahead and erase what we have here. So what we had, how about we let's use green. So we had our function f of x, which was 3x minus 5, and then we had its inverse. Was x plus 5 all over 3. Let's compose these functions together and see what happens. So let's compute f of x, and then let's do its inverse. Okay, well, let's see what's going to happen here when we compose these functions. Okay, what are we going to get? Well, we have our f inverse function. Okay, and what are we plugging into it? We're plugging in f. So we're plugging in the 3x minus 5. Okay, so this is going to be equal to, okay, well, wherever I see an x in f inverse, I'm going to replace it with a 3x minus 5. So what we'll get here is we're going to get a 3x minus 5, and then we're adding 5, and we're dividing it by 3. So I'm just, where this x is, I'm replacing it with a 3x minus 5. Now notice what happens. Okay, we're going to get a 3x minus 5, I'm just going to switch all to green now, plus 5 all over 3. Well, negative 5 plus 5, that's just 0, so we're just left with 3x over 3. Look, we get out x. When I compose these functions together, I just get back out x. These must be inverses. They undo one another. Similarly, what if we do it the other way? Okay, let's say we first start in the inverse. So and then we plug it into f. Let's do it the other way. Okay, what are we gonna get? We'll have f, and then what are we plugging into it? We're plugging in f inverse, so x plus 5 all over 3. Okay, so this is going to be equal to a 3. Okay, I'm going to replace this x with an x plus 5 all over 3. Looks like minus 5. Okay. Let's notice that these 3's cancel each other out, and we're just left with, let's switch to red, we're just left with an x plus 5 minus a 5. These cancel each other out, and we're just left with x. Woo! They work! These functions undo one another. This is a great way to check your work. What I'd like to do for the rest of the video is just get us some practice with with finding inverse trig functions algebraically. So let's go ahead and do that. Okay. Let's do a couple different examples. Okay. let's go ahead and algebraically try to find inverse functions. So let's say that we have the function, let's say it's f of x, let's say it's I don't know, how about 5x minus 7 all over, I don't know, 3. Or how about 4? Sure. Okay, go ahead and pause the video and give a shot at finding the inverse of this function. Okay, let's do it. So what we're going to do here is we're going to first flip out of function notation. So here we'll write y is equal to 5x minus 7 all over 4. So now if we want to find the inverse, what do we know about inverse? We know that the domain and range flip-flop, so our x and y values are going to flip-flop. So now my y's become x's and my x's become y's. Okay, so now we want to solve for y. So we'll multiply both sides by 4. Whenever you see fractions in an equation, you should always clear them. So we're going to get out a 4x is equal to 5y minus 7. Okay, let's add 7 to both sides. So we'll end up getting out a 4x plus 7 is equal to 5y. Okay, now we can divide both sides by 5. Let's divide both sides by 5. And now we're going to get that y is equal to, looks like 4x plus 7 all over 5. This is the inverse. So let's flip back out. Let's go back into function notation. I want to remind ourselves that this is the inverse, f inverse of 4x plus 7. This here is the answer. Go ahead and try to compose these on your own to really show that these are inverses of one another. Let's do another example. Okay. Let's say we have the function. Let's say it's f of x. Let's say it's equal to, how about 9 minus 7 times the cubed root. 7 times the cubed root of, how about 2x? Go ahead and give this a shot. Try to find the inverse of this function here. Okay, let's do it. First thing we're going to do is we're going to flip out a function notation. So y will be equal to 9 minus 7 times the cubed root of 2x. Okay, I need to solve for x here. So I'm going to go ahead and try to isolate this cube root piece here. So let's first subtract 9 from both sides. Well, I guess let's pause here. I want to talk about the inverse. I need to flip-flop my x's and y's. So if we're on the inverse, the x's and y's flip-flop. And now we want to solve for y, and I want to isolate this cube root piece. So we'll subtract 9 from both sides. So we'll get an x minus 9 is going to be equal to a negative 7 times the cubed root of 2y. Okay, we'll go ahead and divide both sides by negative 7. Okay, so we're going to get a x minus 9 all over negative 7 is going to be equal to, looks like the cubed root of 2y. Okay, before I go any further, this x minus 9 divided by negative 7, there's nothing wrong with that, but it's slightly driving me insane. I usually don't like to have negatives in denominators, and you can move a negative wherever you would like in a fraction. For example, if you have, let's say, negative a over b, that's the same thing as negative a over b, which is equivalent to a over negative b. So I can move the negative wherever I'd like in a fraction and it's equivalent. So what I'm going to say here is I'm going to actually move this negative to the numerator. So instead of an x minus 9 over negative 7, I'm going to keep a positive 7 in the bottom and put the minus sign right here. And now this minus sign will distribute into the x minus 9, so I'm going to get a negative x plus 9. Essentially, this is just going to flip the order of subtraction. So this is equivalent to a 9 minus x all over 7 is going to be equal to the cubed root of 2y. Okay. I just think this looks prettier to my eyes. Okay, so I got to figure out how to undo a cube root. Well, how do you undo a cube root? We cube it. Essentially, I'm applying the inverse function to the cube root. So we're going to cube both sides. So let's bring that over here. So we're going to get looks like a 9 minus x all over 7 quantity cubed, and that's going to be equal to a 2y. To finish the job here, what I'm going to do is you can either divide both sides by 2. I have this kind of fraction piece here. So instead of dividing by 2, we could equivalently multiply by a half. I think it's just going to make it look nicer. So what we'll have is we'll have that our y is going to be equal to a 1/2 times a 9 minus x all over 7 quantity cubed. This is the inverse function. We could write this as, now we're going to flip into function notation, so this is the inverse, so f inverse of x is equal to 1/2 times a 9 minus x all over 7 quantity cubed. Okay, let's move this up here. So I'm totally fine with you leaving your answer like this. But you could write it in a different way. So see, we have found out that our f inverse of x was equal to 1/2 times a 9 minus x all over 7 cubed. If you would like, there's a nice property of exponents that x over y cubed, or x over y really to the nth power, is equal to x to the n over y to the n. So this would be equivalent to 1/2. Again, this is a completely fine answer. Just trying to give you another option on how to write this. This would be the same thing as 9 minus x cubed all over 7 cubed. What's 7 cubed? I don't know. I don't know what 7 cubed is. Whatever 49 times 7 is. 7 cubed. So this would be the same thing as 1/2 times a 9 minus x cubed. Let's see. 7 cubed is 343. And now if we multiply these fractions together, I could have a 9 minus x cubed. 343 times 2, we get out 686. So this is completely fine to write it like this. You could also write this as 1 over 686 times 9 minus x cubed. Really, if you wanted to write your answer like this, if you wanted to write your answer like this, or if you wanted to write your answer like this, all would be equivalent. Let's do another example. Okay, let's say we have g of x is equal to, how about 3 times x minus 4 quantity cubed plus 5. Okay, take a second and try to find the inverse of this function. Alright, let's do it. So the first thing I'm going to do is I'm going to flip out of function notation. And then what we have for inverses is that the x and y's flip. So maybe I'll flip to another color. 3, and this is going to be a y minus 4 cubed plus 5. So this is now the inverse function. And now what we want to do is we want to solve for y. So I'm going to go ahead and try to isolate this y minus 4 cubed piece. So to do that, it looks like we could subtract 5 from both sides. So we'll get a x minus 5 would be equal to a 3 times a y minus 4 quantity cubed. We could then divide both sides by 3. These would cancel. So we'll get that x minus 5 all over 3 is equal to a y minus 4 cubed. Now I need to undo a cube. To undo a cube, we cube root. Okay, so the cube root and the cube cancel each other out. They're really inverses of one another, and that's why they're canceling each other out. So we now have a we have a y minus 4 is equal to the cubed root of x minus 5 all over 3. Now our last step is to add 4 to both sides. So we'll get that y is equal to the cubed root of x minus 5 all over 3 plus 4. This is the inverse. So we'll write g inverse of x is equal to the cubed root of x minus 5 all over 3 plus 4. This is the answer. Okay. Let's do another style or another flavor of these problems. Specifically, finding inverses of rational functions can be algebraically tricky. So let's see some examples of that. Okay. Let's say, for example, that we have, let's say we have a function f of x is equal to 2x plus 3 all over x minus 1. Go ahead and pause the video and see if you can try to find the inverse of this function on your own. Okay, let's do it. First thing I'm going to do is I'm going to flip out of function notation. So 2x plus 3 all over x minus 1. Now we want to talk about the inverse function, so the x and y values flip-flop, so my y's become x's, and my x's become y's. Notice that there are two x's here. And now I want to try to solve for y. Now what makes this tricky is that there are multiple y's here. But don't be scared. What we need to do here is you should just recognize that I have an equation, or I have an equation that has fractions in it. Whenever you have an equation with fractions, just always clear them. Always clear them. So let's multiply both sides by my y minus 1. Let's clear those fractions. Okay, so now we're left with a y minus 1 times x is equal to a 2y plus 3. Okay, now notice that I have y's on the left side and y's on the right side. Now what we want to do here is I want to try to bring all my y's to one side of the equation and all my x's to the other side. That's going to be our strategy when we're solving. Really, when you're solving for any variable, you want to always bring that one variable to one side and all the other junk to the other. Now, I want to bring all the y's over, but notice that this y minus 1 is kind of locked up in this multiplication with x. We would like to free this y minus 1 from this multiplication. To do that, we could distribute in this x. So we're going to now get a yx minus x is equal to a 2y plus 3. Now we just need to sniff out our y pieces. Yep, that smells like y. No. Yeah. That's got a y in it. And nope. So all this green I'm going to bring to the left, and all the other stuff I'm going to bring to the right. It really doesn't matter what side you move them to, but I'm just going to bring all the y's to the left. So how am I going to do that? We're going to subtract 2y from both sides. Okay, let's bring this up over here. So now we're left with a yx minus the 2y. What I should also do is add x to both sides. We're going to kind of do two steps here. I want these y's all on one side and all the other stuff on the other side. Okay, so we'll have a yx minus 2y, and then we're going to get on the right-hand side, we're going to get a 3. We're going to get a 3 plus x. Okay, so why was it helpful for us to bring all the y's on one side? What was really our motivation to do that? I can factor out a y. There's a common y in both these. I can take something that looks like two y's, I can make it have one y by factoring it out. That's why we want to bring all the y's to one side, so I can factor that sucker out. So now we're going to get a y times a x minus 2 is equal to a 3 plus x. Now how do I finish solving for y? We'll just divide everything by x minus 2. By x minus 2. These will cancel, and now I have that y. That y is equal to 3 plus x over x minus 2. And here we have it. Here we have it. This is the inverse. This is the inverse. This is the inverse. 3 plus x over x minus 2. Here we have it. The inverse function. Here we have it. Okay, let's do one more example of practices of finding the inverse of a rational function. Let's do one more. Okay, let's say we have the function. Let's call it h of x. Let's say h of x is equal to, let's say it's 4x minus 2 all over 3x plus 1. Go ahead and pause the video and give a shot at solving or finding the inverse of h. Okay, let's do it. I'm first going to get out of function notation, so I'll write y is equal to 4x minus 2 all over 3x plus 1. Now if we want to start talking about the inverse, the x and y's flip-flop, so this y now becomes an x, this x becomes a y, this x becomes a y, and now, since we're talking about the inverse, I want to be able to solve for y. So let's do it. Let's solve for y. Okay, what are we going to do? Man, there are fractions in this equation. Clear them. Clear them. I've been doing math for a long time and I'm grossed out by fractions. Man, if I could get rid of fractions and not have to deal with them, I'm all for it. I'm all for it. Get rid of these fractions. So now we're left with a 3y plus 1 times the x is going to be equal to a 4y minus 2. I want to bring all the y's to one side. I need to free this 3y plus 1 of this multiplication, so let's distribute in this x. So we'll be left with 3yx plus x is equal to a 4y minus 2. Okay, now we'll just sniff out the y pieces. Yep. Okay, and now we're going to move them all to one side of the equation. Okay, so let's move that up over here. So let's see, we'll have a 3y minus x. We're going to subtract 4y from both sides. And that's going to be equal to, well, I have a negative 2, and we're going to subtract an x. So I moved all the y's to the left-hand side, all non-y pieces to the right-hand side. But the beauty of doing this is we can factor out this y. So we'll have a y times a 3x minus 4 is going to be equal to a negative 2 minus x. To finish the job, let's divide both sides by 3x minus 4. Okay, let's bring it down. Let's bring it down over here. So now we have that y is equal to a negative 2 minus x all over a 3x minus 4. Let's go back and use function notation. This is the inverse. It's the inverse of h, so we'll write h inverse of x is equal to a negative 2 minus x all over a 3x minus 4. And this is the answer. Now, I just want to comment on just some style. I'm not a big fan of all these negatives that are going on. Even while this is 100% a totally correct answer, I just don't like these negatives. I'm going to go ahead and factor out a negative. So now we're just talking style points. Okay, let's factor out a negative. We're left with a 3x minus 4. I'm actually going to move that negative to the bottom. Let's erase some of this over here. Okay, I'm going to move the negative to the denominator. So another way I could write this is h inverse of x. Well, we're going to write, how about a 2 plus x. I'm showing a lot of gory detail here. I'm going to move the negative to the bottom. 3x minus 4. And now I could distribute in that minus into the parentheses, but that's just going to end up flipping the order of subtraction. So 2 plus x all over a 4 minus 3x. So for me, in my eyes, I just think this looks so much prettier. For me, this just looks nicer than this version. These are both equivalent. Not one is more simplified than the other, but my eyes are at rest My eyes are at rest when I look at this one. It just looks so much nicer to me. Okay. So what we're actually going to do in the next video is we're going to start thinking about the graphical properties of inverse functions. We'll see you there. Take care.